Now let's relate delta G, it's not a delta G, let's try that again, delta G to K. At equilibrium, everything is reversible. We consider delta G to be 0, and Q is the same as K. At equilibrium, we've defined those. So if we take that equation from the last video, if your brains have recovered from that, if we sub in these equalities in here, we get 0 is delta G plus RT ln K. We can now move the RT ln K to the other side and get delta G at standard conditions is negative RT ln K. And so we can rearrange this as well. If we do some magic math, ln K would be equal to delta G over RT. And if we want to do the exponent, we can get that as well. Just like EA to the EA over RT, right? Very much the same. So we can relate the equilibrium constant now to the delta G. And that's extremely useful because now we can calculate K at any temperature. At any temperature. And that's the whole point of all of this, is that we can establish a way of finding out the equilibrium constant at any temperature with the understanding that we don't have to do experiments about that. We don't have to plug in all this nitrogen and hydrogen and hope we can get the ammonia at the end, right? We can calculate K at any temperature by using delta G. So delta G is something we can calculate using standard delta G values, plug in the new temperature for our system at equilibrium, and poof, we will end up with an equilibrium constant. This is amazingly useful. Let's use it. Let's calculate Kp at 25 degrees Celsius for our favorite reaction. Pretty sure no other reactions exist in chemistry, only this one. So it's a little obnoxious, isn't it? Let's see if we can calculate this. So at 25 degrees Celsius, we've already calculated delta G, right? It's negative 32.8 kilojoules per mole. We've calculated this before. We can again either use the back of the book, delta G values, products minus reactants, done, or we can use delta H minus T delta S. Once we have this, we can go ahead and figure out the K for this, right? By plugging in our values. So the equilibrium constant, Kp, would be equal to E to the 30 to 800. You want to spell all this out just like we do with activation energy, because we have kilojoules here, but our R is in terms of joules. 8.314 joules, and then 298 Kelvin. In doing so, we can say our equilibrium constant. We have to just do all this stuff. So E to the 30, I'm going to make sure I use parentheses because I always mess this up. 32,800 divided by 8.314. Nope, not going to sneeze. I hate that, don't you? It's like the worst. Okay. Hopefully this is plugged in correctly. For this, I get an equilibrium constant of, I've got here a really big number. Oh, and indeed I'm correct. Okay. So 561724 is our equilibrium constant here. And so we're going to be able to put that in sig figs. Let's say we've got 3 sig figs here. So 5.62 times 10 to the 1, 2, 3, 4, 5, fifth power. So we will have calculated our Kp. So this reaction very much favors the products. And we can tell because it's spontaneous, right, at this temperature. We've seen that. So that's how we can kind of use all this fun stuff. We can also calculate it at a higher temperature. Let's see what we get here. Let's say, how about at 1,000 degrees Celsius? Let's do it. Kp equals E to the 32,800 over 8.314 times 298 is going to be 1,273. Let's go ahead and do this one. So E to the 32,800 divided by 8.314 divided by 1273 equals, 22. So our reaction is becoming less and less favorable as we increase the temperature. And let's see if that makes sense to us. We saw for this reaction, we are having a negative entropy, right? We are decreasing the number of gas particles, so we're having a negative entropy. We saw, however, that this was an enthalpy negative exothermic process. There we go. Can't remember the word. So we have a negative delta H, a negative delta S. We see that this is spontaneous at low temperatures, according to this, negative for both. So as we keep raising the temperature, eventually we'll reach the point at which it is no longer spontaneous. So you can finally stop our favorite reaction from happening by heating this all the way till some crazy high temperature, maybe 1,500 degrees Celsius or something. So that's the whole takeaway from all this. We want to use this handy-dandy equation to figure out equilibrium constants for any reaction at any temperature. And so that's it for thermodynamics. What a crazy, wild ride this has been. The math here is a lot easier than it was for our equilibrium and acid-base and all that, but still certainly a bit of math. So still, you should be going through all of these videos with your calculator, plugging things in as you go to make sure you can do them on your own. And so that's it for thermodynamics.